before right before lunch.
We have this last talk in the morning session. We have the fortune to have Jiaqing from Caltech, who is going to talk about deep sample, deep states preparation for commuting Hamiltonians.
Okay, thanks for the introduction. I'm Jiaqing from Caltech. Today I'm going to talk about the algorithm for preparing deep states for commuting Hamiltonian. But we map it to a classical Gibbs sampling task. So this is joint work with Yongwu Huang from Harvard, and it's our tradition to put course pictures on the first night. So to begin with, I wish to talk about some motivation. I'm a little bit surprised nobody talk about the motivation, but so this slide can be interpreted as a summary of yesterday's panel discussion. So first let's recall what's Gibbs states. Like Gibbs states is some states which describe quantum minimal system at finite temperature. So like the reason we care about Gibbs states, like we are interested in Gibbs states, is because there are many potential applications. As mentioned in like yesterday's panel discussion, here I wish to briefly mention 3 of the possible like application of Gibbs states. So I mean the first one would be by the definition of Gibbs states is related to many body systems. So naturally it might be applied in physics. Like if you have a Gibbs states preparation algorithm for some like interesting Hamiltonian, you might be able to use this algorithm to study phase diagram or to study some like thermodynamic properties. And besides, like as you may heard of, Gibbs states are also used in machine learning. Like for example, Birdman machine is just a Gibbs states of EC model, and the people in quantum also propose quantum Birdman machine, which is based on transverse EC model. And besides those 2 things, like in fact, Gibbs states can also be used in optimization. So there are some like STP algorithm which use Gibbs sampling as a subroutine. So if you can have an algorithm which can speed up like the Gibbs sampling task, you might be able to like improve the performance of STP. So that's our initial motivation, like why we are interested in Gibbs states. So in this talk, our main goal is to try to design good Gibbs sampler, where Gibbs sampler just refers to like some algorithm to prepare Gibbs states. So what does good mean? So here good refers to 2 requirements. One is correctness, which means if you want your algorithm to be useful, at least you wish your algorithm will converge to Gibbs states finally. So formally it says like you want the algorithm converge to Gibbs states in finite time. But here finite time might be is a very big term. Like it might be 1,000 years. So that's not good. So a further requirement would be efficiency. Like we wish our Gibbs sampler is not only correct but also fast. So we wish it to converge in Hamiltonian time. So that's the 2 requirements for designing a good Gibbs sampler. You may ask, okay, what's state-of-art results? Like what do we know now? So for the correctness part, like recent years, there has been like a lot of exciting progress in this direction. So currently we have like 2 types of Gibbs sampler, which is correct. One is inspired by, so you can check the 2 introductory talk in the beginning of this workshop. So like one is depth generator inspired approach, which is done by many of the audience here. And another one is more similar to like classical multipolinies. And this one like also is done by Anne and Sandy, and our work is based on Kristen's paper. So that's the correct part. So compared to the correctness part, where there has been a lot of exciting progress in the last few years, for the efficiency part, less is known. So for the efficiency part, if we only looking at classical Hamiltonian, like we know a lot of things because the classical Gibbs sampling task has been studied for at least 40 years or even more. So like there there are already a lot of knowledge like which you can learn from classical Hamiltonian. So roughly speaking, like so people have already designed efficient Gibbs sampler for classical Hamiltonian in many different regions, like 1D at any temperature, like 2D at high temperature, and 2D at low temperature for some Hamiltonian. So like people know a lot about classical Hamiltonian. And if you ask whether we have efficient Gibbs sampler for quantum Hamiltonian, I have to say like very few is known. So much of recent efforts are still working on like a special case, which is commuting Hamiltonian. So for example, 2 days ago, Jiang just gave a talk on like Gibbs preparation for Toric code. So this is a special case of commuting Hamiltonian. That's also a very nice talk, and you can check the videos. So okay, let's back to our question. So I'm saying like many recent efforts are focusing on commuting Hamiltonian. So you may ask, what is commuting Hamiltonian? So in a general definition, commuting Hamiltonian is a local Hamiltonian such that all the terms commute with each other. So I mean, commuting Hamiltonian is a subclass of local Hamiltonian. So people study it because of 2 reasons. The first reason is, I mean, obviously it should be much easier than the general case. So like the commuting property make it easier to analyze and to, I mean, get some results and to start with. But besides it, the reason is simpler. Another reason like commuting Hamiltonian is interesting is because in fact it's non-trivial. So in the beginning, you might think that commuting Hamiltonian is very close to classical system. In fact, that's not true. So commuting Hamiltonian, in fact, can capture some very highly entangled system. So for example, like Toric code. So what do I mean for highly entangled? So for classical Hamiltonian, everything is diagonal. And I mean, it's diagonal in the computational basis. So for commuting Hamiltonian, like its eigenstates can be very complicated. So for example, like it's well known that for Toric code, like you cannot prepare the ground state by any constant depth quantum circuit. So it's really some very quantum system. So that's why that's one reason why commuting Hamiltonian is interesting. So this is just the definition. Oh yeah. That's definitely true. Yeah. So okay. So in this talk, you should interpret every commuting Hamiltonian as commuting local Hamiltonian. Yeah. Thanks for the clarification. So today's talk will be on something like efficient Gibbs samplers for commuting Hamiltonian. So there are a lot of previous work. So to avoid confusion, I will first talk about previous work and our work in a very high level. And after that, I will talk about our work in more details. And then I will give a more detailed overview of previous work and compare it with our work. So that's the plan of the following talks. So first, okay, let's first talking about previous work and our work in a very high level. So recall that our goal is to design efficient Gibbs sampler for commuting Hamiltonian. So what does previous do? So first recall that we mentioned based on Davies generator, you can design a correct Gibbs sampler. So most of previous work is trying to analyze this Gibbs sampler, like to analyze whether it's efficient or whether you can design some kind of variants of Davies generator to make it efficient. So in summary, like most of previous work is trying to generalize the proof technique from classical to quantum. It's like they try to they look at the classical proofs for fast mixing and see whether it can be modified to prove the fast mixing for Davies generator. But one thing I want to emphasize is like, in fact, these kinds of generalization is very non-trivial because Davies generator is a quantum operator, and analyzing its spectral gap is quite complicated. Any question? Okay, yeah. So that's the first thing I want to mention. Like I think it's non-trivial, and the second thing is like I want to emphasize So previous work generalized some of the classical results to quantum. It's not everything, which I will give a more detailed overview later. So you may ask, okay, what do we do? So from a high level, we also try to generalize the classical result to the quantum case, but in a more direct way. So what do I mean? So we are not using Davies generator. Instead of using Davies generator, we directly use the classical Gibbs samplers. So roughly speaking, our algorithm will work as follows. So first, we will, to give a commuting Hamiltonian, we will compute the classical Hamiltonian. And the first thing we do is like do a classical Gibbs sampling for the classical Hamiltonian and get a bit string. And then based on this bit string, we do some simple quantum operation. So for simple quantum operation, I mean, like either you prepare a constant depth circuit or you do a chain of single qubit unitary. So that's all the quantum operation we need. Any question? Okay. Yeah, so this is just a, so okay, so next I want to mention, like, I mean, so this algorithm looks very simple. And you may ask, okay, is it powerful? So in fact, we will show that we are able to replicate many state-of-art results, many state-of-art like efficient Gibbs sampler for commuting Hamiltonian. And besides, we can also prepare, so instead of, I mean, we can not only replicate known results, but we can also like, yeah, do something which is not unknown before. So this is a high level. Yeah, I just want to emphasize, like, if you need to be confused about what I'm saying now, that's totally fine, because this slide is just for high level picture, and I will talk about the details later. So like in summary, previous work is trying, based on Davies generator, they try to design efficient Gibbs sampler. Our work is like we directly use classical results. Okay, so then let's go to some like more this is not taking, okay. So let's talk about our result in more details. So to explain our results, let me first explain what is Gibbs sampling reduction. So we see there is a Gibbs sampling reduction for commuting Hamiltonian H. If you can efficiently compute the classical Hamiltonian HC such that you can use the Gibbs sampler for the classical Hamiltonian to prepare the Gibbs states of the commuting Hamiltonian. So what do I mean? So more formally, it means we say there is a Gibbs sampling reduction from commuting Hamiltonian H to a classical Hamiltonian HC. If you assume there is an algorithm to prepare the Gibbs state for classical Hamiltonian in time t, then you can utilize this algorithm to prepare the Gibbs states of commuting Hamiltonian in time t plus a small overhead. So in our theorem, like the small overhead will always be either On or On square, where N is the number of qubits. So that's a definition of Gibbs sampling reduction. Is there any question? Okay, I'm happy it's clear. So then we are ready to talk about our results in more details. So in summary, like our results is to show there is a Gibbs sampling reduction for various commuting Hamiltonian. So this class of commuting Hamiltonian includes like all the 2 local commuting Hamiltonian and also a large class of 4 local qubit commuting Hamiltonian. So more precisely, for the 2 local case, the classical Hamiltonian will be also 2 local. And for the 4 local case, the classical Hamiltonian will be much complicated. So when I say complicated, I mean it will depend on a notion called classical qubits. So like the form of the classical Hamiltonian will depend on like whether the original Hamiltonian has classical qubits or not. So the classical, you may ask, what is classical qubit? So classical qubit is just a qubit such that all the Hermitian terms acts in as a classical way in its qubit. So I mean, formally it says like all the Hermitian terms will look like, when I say Hermitian, just mean like the terms in the local Hamiltonian. So all the local terms well looks like either 0, 0, 10 or something, plus 1, 1 or something. But here, like implicitly, I assume we are allowed to choose local bases. So that's a definition of classical Hamiltonian, classical qubits. So more precisely, like based on more precisely based on whether there are classical Hamiltonian, like we classify the. So we have two cases for the local case. So case A is like if there is no classical qubit, then the classical Hamiltonian will be. Then we will map a qubit for local classical Hamiltonian. Then we will map a qubit for local commuting Hamiltonian to a QD to local classical Hamiltonian on planar graph.
Explain again what you mean by no classical qubit.
So this is the definition of classical qubits. That means like there's no qubits, which is classical. Okay, let me give another.
So does it mean like in the thermal state there's no coherence in these qubits?
I mean, okay. So probably intuitively you might just understand is there's no term looks like Z. Like there's no. So for example, a counterexample of Hamiltonian classical qubit will be Toric code. So every term looks active quantum way. So okay, basically I'm just saying like the. Okay, so question again.
Yeah, but please go ahead. Yeah.
There's
Please continue.
Oh, okay.
I'm listening.
So what do you mean on the classical side it involves a qubit? Like if you go to like two sides later, like you're mapping to a classical Hamiltonian which involves qubits. So what does that mean?
Yeah, it means something like I group some qubits into a QD, and then the Hamiltonian will become two local.
So because it's a classical, right? So you're thinking about there's some color on one side.
Yes. Yeah. So like I mean.
It's like a plus model.
So it's not exactly possible, but it's some analog of that. Yeah. So I map it back to classical, but I sacrifice by increase the dimension.
So you said the Toric code has classical qubits or doesn't have?
Doesn't have.
It doesn't, but it has Z terms though.
So it's like if a qubit is classical, it means every term acts as Z.
Ah, okay.
Yeah.
So it means what?
So it is similar to the concept that all the terms act as Z on this qubit. It's all the terms Z tensor blah blah blah.
So for this definition of classical, are you allowed to change the basis?
Yeah.
On that single qubit.
Yeah.
But I mean, but this change of basis could be like decoupled of. Okay, no, sorry.
Just rename, right? Yeah.
So after change of basis, it cannot be something like Z.
Yeah. Or Z plus identity, because identity is not important in the Gibbs states. So like this is the example of this class of Hamiltonian. For example, an example is defective Toric code, which is Toric code with arbitrary coefficients. So for defective Toric code, the corresponding classical Hamiltonian will be empty. So our algorithm will be able to prepare the Gibbs states for defective Toric code in time 0 plus O(n) square. So in comparison, like previous talk, and at any temperature, so our algorithm, this reduction in fact does not depend on temperature. In comparison, the algorithm based on Davies generator, which Jiang gave on Tuesday, it has runtime as O(n) to the 4th. But of course, like I wish to emphasize that in fact those two results are somehow incomparable, in the sense that like our algorithm is just for preparing Gibbs states, so we don't really like cover the connection to Lindbladians. Just H is 0. This Hamiltonian is 0. toric code with arbitrary coefficients. So standard toric code is z, x, x, x. I allow arbitrary coefficients inside of x and z term. It's like, I mean, arbitrary, like not necessarily plus minus, arbitrary real value.
Still need to be frustration free.
No. So it's something. So okay, commuting Hamiltonian is always frustration free based on your definition. So one thing I want to mention is like, yeah, something I want to mention is like you might want to compare this model to Ising spin glass. I want to emphasize this model is very different from. So toric code is very, very different from Ising model.
For every realization, you get some kind of a. I don't understand what you mean by arbitrary.
I just mean like, so this Hamiltonian is fixed. It's like, yeah, it's like, for example, like in just like some, like you can have the n coefficients. So you have a fixed, the first fixed is the manual, and you can prepare the Gibbs set of this Hamiltonian. That's what I mean.
When I say it's different from Ising spin glass, I mean, in there we have the coefficients can be both positive and negative. That's great trouble, right? So here, do you also have both positive and negative coefficients?
So what I mean is like, even you allow like arbitrary coefficients, finding the ground state is an easy task in this case, because this toric code really behaves different from Ising model. So it doesn't suffer the hardness in Ising model. Okay. So that's an example of case A. If we allow classical qubits, the situation will be more complicated. So it's a bit technical to explain why the situation becomes complicated. But roughly speaking, like in this case, we need to make an assumption that all the quantum terms are uniformly correctable. So for the quantum terms, like roughly speaking, is some term like far away from classical qubits. So it's like we need to have a good control for the terms which are far away from classical qubits. And the one thing I want to the thing I want to emphasize is like for this case, like the classical Hamiltonian will be qubit, but it will no longer be 2 local or 4 local. Like the classical qubits will increase the locality of this classical Hamiltonian. So that makes everything more complicated. So this is the summary of our results. As I said, like our theorem is just give sampling reduction, and combined with known already like existing classical Gibbs sampler, then we will be able to give a Gibbs sampler for commuting Hamiltonian. And although this, although based on the table, you may think, okay, it sounds not very powerful, but in fact, we are able to replicate many sets of other results. So I think in fact, that's the main motivation why I'm doing this. So okay, let's sorry. So if it's based on what's your goal. So if our goal is to prepare Gibbs states in a faster way, then it's comparable, like it's just a runtime, compare runtime. But if you want to know something about the Lindbladian dynamics, like for example, I remember they're talking about something related to quantum memory. That's something. So like if you use Lindbladian dynamics, there will be some connection between how thermal noise influences this system. Yeah, so that's something we don't cover.
Starting from a fixed thing, how to prepare a fixed thing, starting from anything.
Yeah. Yeah, exactly. Thanks for the explanation. Any other questions?
Jiaqing, your Gibbs sampler for the commuting H is going to be quantum or classical? Yeah.
For what? For the classical part or for quantum?
What you get at the end, the Gibbs sampler for the commuting.
It's a quantum algorithm. Yeah.
This is like a classical algorithm which gives you the bit string, then you do lookup to generate the circuit. Is that correct?
Yeah. So the algorithm is just okay. Let me recall what's the algorithm. So the algorithm is like you first do a classical Gibbs sampler and get a computational basis. And based on this computational basis, you either prepare a constant depth circuit or do a chain of ponies or a chain of single qubit unitary. So this is the quantum part of the algorithm. Okay. So this algorithm looks quite simple. And you may ask, okay, how does it compare to previous results? So to explain previous results, let me first recall some definitions. So as many previous work already mentioned, like the key quantifier for efficiency is mixing time. So roughly speaking, like mixing time is a number of iterations required to prepare the Gibbs states. So for example, if you use Davies generator or if you use a continuous time classical Markov chain, the mixing time is a minimum time t such that after some evolution, after time t, you will be able to close to the Gibbs states. And for simplicity, we just say to the precision to be 1 pony. So one thing I need to explain is why I use the term iteration rather than time of t required to prepare Gibbs states. It's because if you want to simulate this process on quantum computer, typically you need to pay some additional cost. So that's what I mean for iterations. But anyway, based on mixing time, in the following, I will talk about 2 different efficient Gibbs samplers. One I call it fast mixing, which means the mixing time is fully in the system size. And another one is called rapid mixing, which means the mixing time is logarithmic in the system size. So in fact, this is why I emphasize the mixing time is number of iterations, because you won't be able to, you won't really prepare the Gibbs states in point log time. You always need to pay some additional cost. But that's two situation of efficient Gibbs sampler. So now we are ready to talk about previous work. So recall that so we were trying to review what's the known results for efficient Gibbs sampler for commuting Hamiltonian. So let's begin with a classical case. So roughly speaking, classical, whether they are efficient Gibbs sampler or what's the performance of your Gibbs sampler depends on the geometry. It's whether it's 1D or 2D, and also depends on the temperature, whether you are working on low temperature or high temperature. So roughly speaking, I think the previous result can be classified as 2 cases. One is relatively easy, and one is harder. So for easy, I mean for example, for 1D, any temperature, and 2D, high temperature. Those cases will correspond to disordered phase, which basically means there's no need to choose some special jump operator. It's no matter what you did, Gibbs sampler associated with local jump operator will be fast mixing. But on the other hand, if you go to higher dimension, higher than 2, and for low temperature, the case will become harder. So when I say harder, it's the Gibbs sampler associated with local jump operator will meet something called critical slowdown, which means those Gibbs sampler will be slow mixing. You can prove the spatial gap will be exponentially small. So for those harder case, you need to do something more fancy. You need to design some variants of Gibbs sampler. So for example, in the classical world, people will use Swenson-Wang algorithm, which is a cluster update, which basically means you use a very long local jump operator, and or some other methods, for example, Baranow's method. So there are something in the classical world. But in summary, Baranow's method. So so this method can be used for both classical, both high and low temperature. It's something interpret some it's something, okay, so the typical way of using it is interpret partition function as a complex function and use Taylor series to do something. But that's a very standard version. But if you ask me, so I cite this. I can give a reference if you are interested. It's something.
Explain.
Yeah, that's the original way of using this. Yeah.
And Swans is supposed to work for any temperature, and
There was a critical slowdown as well.
It's another model.
It's different models. You are right. Yeah. So this is for easy model. If you increase the dimension, go to port model, Swiss one will also meet critical slowdown in low temperature. So this is another method which can do like low temperature Gibbs state preparation for port model, but not for everything. Like that's for it requires the dimension to be higher than something.
Question.
Yeah.
For 1D at any temperature, you mean easy? Do you mean like for any beta, like even beta is like a super polynomial? It's
Yeah, that's a great question. So I need to clarify. So here I mainly mean constant. So when I say any, I always assume the temperature is a constant. Yeah, that's a great question. Yeah, so that's what we know for classical world. But in summary, it's like for classical world, we know a lot of things. It's like we know, yeah, low temperature. We also we know high temperature. We also know how to do low temperature, and and also this is not a complete survey. Like there should be a lot more results. So then next, so like if you are interested in the classical case, you can check Reza's talk on Tuesday. They give some techniques in, which is very helpful. Okay, so this is the situation for classical world. You may then let's review what happened in quantum world. So previous work has successfully generalized many results to the quantum case. But most of them are either relatively easy region, is in the disordered phase case. And besides those cases, so according to my knowledge, like I think there's no results which try to generalize Wilson one to general to the Hamiltonian at low temperature. There is one exception case. Okay. There's one exception case which is Zhiyang's talk. So they try to prepare like low temperature Gibbs states for 2D Toric code. So this is concurrent work. So that's the previous work. So our work, as I mentioned, like our work is use the Gibbs sampling reduction and then combine it with the classical Gibbs sampler, and which directly use classical Gibbs samplers. So this makes us, be able to replicate the either region and also some hard region. As long as there are some efficient Gibbs sampler for the corresponding classical Hamiltonian, and also like for the Toric code case, we will be able to prepare the defective Toric code in time O(n) square. And also I want to mention, like, so this is the mixing time, and this is the real runtime. So our runtime is really O(n) square. Yeah. So our argument is very, very different. Yeah, it's nothing to do with. And besides this table, so this table is on a special case of our algorithm. So in fact, our Gibbs sampler can work for more general case, more general to the full local commuting Hamiltonian, like as long as there exists some efficient classical Gibbs samplers. So as I said, like I didn't do a like very thorough review of classical Gibbs samplers, but there should be a lot of them because that's a big area. So this is a summary of our results. Like any question here?
Stupid question. Did you come up with the term defective Toric code?
No, it's in the definition.
Yeah.
Like the first time I see the definition is in like Davies' paper. So in fact, like most of the inspiration of the techniques comes from the complexity of commuting Hamiltonian. Yeah.
Can I go the other way as well? I have a classically efficient Gibbs sampler and then construct a bunch of quantum that I can pathetically say.
So you want to use quantum Gibbs sampler to
No, I just wanted to understand like for which classes of Hamiltonians I now have efficient Gibbs samplers. Can I like reversely construct quantum Hamiltonians given a classical Hamiltonian? Quantum.
Yeah, that's a good question. I don't know. Like, yeah.
Maybe also related points. Are there still separation between the sampling of quantum local commuting Hamiltonian versus sampling of classical?
Separation. So yeah, there is a result which says sampling from commuting Hamiltonian can be quantumly easy but classically hard.
So in terms of your result, what does that mean? Like the commuting quantum Hamiltonian there violates some of the structural assumption that you made?
No. So I mean, yeah. So that's something I need to clarify. So I'm using classical Gibbs sampler, but in fact I also use quantum operations.
Oh.
Yeah. So that yeah.
So in your diagram, then the quantum operation is hard.
Yeah. So I mean, for example, I use the ability to constant depth circuit. That's already classically hard.
You describe how your algorithm would prepare the ground state of the just standard Toric code?
Yeah. So first, like this algorithm, so my algorithm does not work for 0 temperature. I cannot prepare ground state.
Okay.
But there is another way to prepare ground state of the effect Toric code.
Right.
Yeah, as I mentioned, like this is very different from instant spin glass. That's right. So you can check the risk paper. Yeah, question? Okay. So that's our summary. And I always want to emphasize like this comparison is only for Gibbs state preparation. Like we don't cover the implication with respect to thermal noise. So okay, before we go into details, also I only have several slides for details. I wish to mention another interesting implication on quantum approximate counting. So this is mainly a complexity question, but it's one of my favorite complexity questions that I wish to mention. So approximate counting is, roughly speaking, is the task of estimate partition function. So this partition function is just like the normalization factor of the Gibbs states. So we see it's a counting because I mean, when you compute the partition function, you add all the Boltzmann weights. So that's why it's called a counting problem. So one of my favorite results in classical complexity would be, you might ask, okay, what's the complexity of approximate counting for classical Hamiltonian? So when I say complexity, I mean like, you might ask, okay, what's the additional power I need? If I have BPP machine, what's the additional power I need to compute the partition function? So one of my favorite complexity results is like classical approximate counting is in BPP to the NP. It's like you only need the NP oracle. So yeah. It's like distinguish K and 2K, something like this. Yeah, and then naturally you can ask, okay, what's the case for quantum counting? Like how far that's quantum approximate counting from BQP? And naturally you might think, okay, it should be something like BQP to something probably QMA. But as far as to the best of my knowledge, I think no result is known in this direction. So our theory gives some like elementary results theory in this goal. So our result is there is a Gibbs sampling reduction for various commuting Hamiltonian. So there is a connection between like preparing Gibbs states and like approximate partition function. So based on this connection, our result implies for various commuting Hamiltonian, the quantum approximate counting is in BQP to some oracle, where this oracle is doing like classical Gibbs sampling. So I want to mention this because I think it's pretty interesting to say whether someone can somehow prove a more general theorem to say some kinds of quantum approximate counting is inside BQP to some oracle, which is reasonable. Sorry. Okay, yeah, I think it's not for me. So okay, that's some complexity results. So let's give a proof sketch. So this proof sketch is very short. But you can find me offline if you are interested. So for the two local case, in fact, it's relatively very direct if you know some kinds of complexity techniques. So this is mainly based on something called structure lemma. So basically, okay, let's skip some details, but go to the final sentence. So very roughly speaking, like structure lemma says you can turn any two local commuting Hamiltonian to a classical Hamiltonian by some constant depth circuit. So I use a quote for the constant. Yeah, it's because like it's a little tricky to define the depths, but it's something simple. That's all I can say. And I also want to mention like there is a constructive proof for the structure lemma, especially because we assume every QD is constant dimension, so you can efficiently find this decomposition. So that's for the two local case. So for the four local case, like since it becomes more complicated, it's because as I said, like because four local commuting Hamiltonian contains a highly entangled system. So which means like highly entangled, the Engin state cannot be prepared by constant depth circuits, which means like you cannot use structure lemma to transform this Hamiltonian to classical Hamiltonian just by a simple constant depth circuit. So instead, how do we prepare the ground Gibbs state of this Hamiltonian? So instead, we somehow modify an algorithm from ground state preparation to Gibbs state preparation. So you may ask how do we do this? So for example, we take Toric code as example. For Toric code, by the definition of error correcting codes, you can prepare the ground state by measure and correct, right? So you begin from arbitrary states, and then you sequentially measure every term, and you get some like measurement value. And based on the measurement value, you do some correct operation to flip it to the right eigenspace. So in fact, we notice this algorithm can be modified to prepare the ground state, prepare the Gibbs state. How do we do that? Is like we begin from a maximum mixed states. We also sequentially measure every term. But instead of doing like deterministic like correction, we do a randomized correction. So for example, like if you, this is quantum algorithm, right? So you begin a quantum state and measure a state and perform a chain of unitary. Yeah, so the algorithm is something like this. It's like if you get, so suppose you are measuring one term, if you get +1, with some probability you will you do nothing. And with some probability you will do the correction. And similarly for -1. And the probability is in fact just some simple thing. So you may ask, okay, why this works? It's because in some sense it's because Toric code is very symmetric. The ground space is very symmetric. And the correction operator, if you're looking at the Engin space, it's a bijection between the corresponding Engin space of +1 and -1. So okay, that's a good question. So first, as I mentioned, like for defect Toric code, the classical component is empty. So this part is just a quantum part.
So you don't need the classical.
Yeah, and here this is not a. So although I use randomized thing, this is not a Markov chain. It's like for every term I only do this for once. There's no iteration. Yeah. No, I just sequentially do one by one. So random is you decide whether you do correction or not. Yeah, so I measure every bracket, but I might not do correction. Yeah, so this in fact captures one idea, and you may ask, okay, well, for more general case, how could we do that? how could we do something similar? Because I mean, for more general commuting Hamiltonian, it cannot be, I mean, as regular as Toric code. So our result is, in fact, based on some complexity result by Davies and his courser. It's like, it's like for qubit for local commuting Hamiltonian, you can also prepare the ground state by a measure and correct approach. So roughly speaking, something like if you remove some term, you can group the qubits and get a two local commuting Hamiltonian. And then, I mean, you just measure and correct. And you can do the same thing for to prepare Gibbs states by noticing there is also a symmetry on the eigenspace. It's like you can also do something like this. Yeah, and final remark is if you have additional classical qubits, you will meet some very strange thing in this algorithm. So that. Right?
This is only needed when you have natural coefficient theory defective Toric. So the positive one should be easier.
For this slide.
Yeah.
So like for the defective Toric code, everything would be very easy. It's like there's no there will be, so the classical Hamiltonian will be empty. So this is a more harder case. It's a harder case.
Could you say a bit why the classical bits are harder? Like seems it's a bit counterintuitive. Like quantum seems a bit harder.
It's because so it's because so in fact so in the beginning I defined like classical qubits as something something like this, but in fact the final definition of classical qubits will be adaptive. It's like if you for example in the beginning you have a classical qubit, you like if you choose the subspace, then some you restrict the Hamiltonian to a subspace, then there will be some other qubits which become classical. So this will hide some information. So classical, so that's why it becomes harder. Okay, so that's my final slides. Thanks for listening.
All right. Questions before lunch?
Could I ask a question? So next talk. So regarding this like approximate counting result, I know you said that like for these classes of Hamiltonians, it's like BQP to this classical sampling oracle.
Yeah.
Can you explain actually like, do we need the quantum computer to compute the partition function here?
In my algorithm or in the.
In your approach.
Yeah. Because my algorithm is more like I get a hint from classical, but then based on a hint, I will do some quantum operation. Yeah, so that's a quantum part.
And those quantum operations, like they will also affect the trace. Cool.
Oh, okay, that's a good comment.
About it, because the CC diver just disappeared.
Oh, okay.
Or is there also like some like quantum Lindbladian type thing on top of it?
Yeah, I should think this more. I think that's a very good comment. Yeah.
Thank you.
This is maybe a stupid question, but what's special about the number 4? Like what happened to the number 3? These techniques are so dependent on order of the
can you say again? I didn't hear.
like 3 local. Yes, for example, if it was 3 local, this technique wouldn't work. Like if there's some this is number 4 special in some way.
So I didn't think about 3 local. So like let me think. So there are some complexity results on 3 local commuting Hamiltonian. I guess. I think so. So this technique will depend on. So the key part is you need this correction operation, be able to exactly map one eigenspace to another eigenspace. So that's something I'm not sure for Q3 case, but probably it's for 3 local case. But that's a good open problem. Probably.
maybe also a bit of a philosophical question. So since your proof technique is based on ground state preparation.
Yeah.
So does it mean that for this kind of sampling algorithm that to be efficient, then first priority is that ground state preparation has to be easy so that the thermal state preparation will be easy for these systems?
Yeah, that's this conjecture.
Oh,
So like,
conjecture already.
yeah. So in fact, I mean, in fact, I think the most powerful part of this algorithm, in fact, comes from the previous secret knowledge in studying computational Hamiltonian. And yeah, so for there are more results which says we can prepare a ground state of computational Hamiltonian, which is not included in this algorithm. Potentially, you might be able to also generalize this ground state preparation algorithm to give the preparation. Yeah, like haven't really think about this very carefully yet.
I would suggest to take the rest of the discussion over lunch, and let's thank the speaker and all speakers.